Right, so very quickly, I'm going to go over the superfluid phase and how you find the scaling. And I'm going to look at the specific example of this 3D n equals 2 theory with phi cubed superpotential. At large charge, we write down an effective action for this theory, assuming that it goes to a CFT and that we have some fixed background charge. A dimensional analysis just gives us one possible term in leading order. This is just the scalar potential with phi to the 3 halves. Writing this in terms of the components of bosons and fermions, we find that fermions decouple and absolute value of phi decouples. And the only thing left over at small energies is this Goldstone boson chi with the effective action d chi to the 3. Using the charge fixing condition, the equation of motion, we can read off that delta of q goes like q to the 3 halves from this effective action. This exactly matches what we call the superfluid phase. So this is d over d minus 1 for a 3-dimensional theory. The second interesting phase is the 3-scalar phase. And again, I'm going to focus on a specific example, which is this time this n equals 2 supersymmetric theory with an xyz superpotential. So solving the f-term equations for this theory, you find a moduli space. So the moduli space has 3 branches. In every branch, one of the fields gets observed, while the other 2 stay zeros. For example, one branch is x non-zero, while y and z vanish. And in this theory, x to the n, this operator is BPS. So its dimension is protected, and it's just given by 2 over 3 times n, 3 dimensions. In addition to due to the BPS bound, for any operator of charge n, this 2 to the 3 over n is also a lower bound on the dimension. And so this is the lowest dimension possible for any operator. And so we find that delta of q is just linear in q. It should be 2 over 3 times q because we have some BPS operators for any value of the charge. So in this phase, we find delta of q linear in q. So delta of q goes aq because we're in the 3-scalar phase. We discussed these 2 phases, the superfluid phase and the 3-scalar phase. And the question I want to ask is whether these are really fundamentally different. So in the superfluid phase, the dimension goes like q to the d over d minus 1. 3-scalar phase, it's just linear in q. And the question is what happens as we try to vary some parameter and go from one phase to the other. Because we call them phases, it sort of sounds like there should be some phase transition, some singularity, and we're going to check whether this is really the case. We want a theory with a parameter tau, which interpolates between these 2 phases. So at small tau, we want to be in this 3-scalar phase where delta goes aq, but at large tau, we want to be in a superfluid phase where it goes aq to the d over d minus 1. And we're interested in what happens in the middle and what sort of transition, what the transition looks like between these 2 phases. This type of analysis has been done before in some specific examples I'm going to review now. So the first case this was done in is in the O2 model, where our parameter tau that we vary is the dimension of the theory. So in the O2 model, we just take a boson with phi to the 4th potential. In 4 dimensions, this potential is marginally irrelevant. So the theory just goes back to the 3 theory. So in 4 dimensions, we just get the 3 phase. While in 3 dimensions, this goes to the Wilson-Fisher fixed point and we get superfluid phase. So as a function of the dimension, you can go from this 3 phase to the superfluid phase. So specifically in the epsilon expansion from 4 dimensions, this has been done systematically and people found this transition and studied it. This is in these papers down here. And they found a smooth transition between these 2 phases in the epsilon expansion as a function of the dimension. Another example where this was done is in the ON model at large n. So in this case, we fixed this parameter tau to be 1 over n. So at small q over n, you see the 3-scalar phase, while at large q over n, you see the superfluid phase, and again, you see a continuous transition between them. The problem is that both these examples are not 100% satisfactory for our purposes. The first example, because the parameter we're changing is a dimension, which is a weird parameter to change in your theory. And in the second example, n is a discrete parameter and not a continuous one. So what we want is a unitary example with a continuous parameter where you see this transition. Good. Then we're going to consider the following 3D supersymmetric theory. We discuss an n equals 2 theory with 3 chiral superfields, x, y, and z. And the potential written down here. So we have the xyz term, plus an x cubed term. So this theory for any value of tau and g has a U1R symmetry, which just rotates all three fields with the same phase. And so we can study the theory at large U1R charge. There are two interesting limits for the theory. So one is tau equals 0. Tau equals 0 is just the XYZ model we discussed before, so it's in the free scalar phase. The other interesting point is tau equals infinity. So there we can throw away this XYZ term and we're left with x cubed plus y cubed plus z cubed. We get 3 copies of this supersymmetric Ising model. Tau equals infinity we expect to be in the superfluid phase. The main point is that you can show using standard arguments like Lee and Strassler that tau is exactly marginal. So tau parameterizes a line of fixed points that connects the XYZ model to this x cubed model. So you can use tau to interpolate between the two phases, between this free scalar phase and the superfluid phase. Because it's exactly marginal, you have a CFT at every point, and so you can use the large charge expansion and study for any value of tau what happens at large charge. One more important comment is that even though it seems like tau equals 0 and infinity are an infinite distance away from each other, the conformal manifold is actually compact, and they're actually a finite distance away from each other. You can see this, for example, by computing the Zamolodchikov metric in the epsilon expansion. Doing this, you also see that this conformal manifold is topologically a sphere. Is a sphere, and so you can think of tau equals 0 as this XYZ point and tau equals infinity as the antipodal point, where you have these 3 copies of the XYZ model, the x cubed model, and they're a finite distance away from each other. It's just 2 antipodal points on a sphere. This model was studied to excruciating detail in this paper by Baggi et al. And in particular, these guys found a duality relating different points on the conformal manifold. So there's a very simple duality that you find by just redefining your fields. So you take x, y, and z to be some linear combinations of x, y, and z. Plugging these back into the superpotential, you can find that for specific linear combinations, you end up with exactly the same superpotential, but with the parameters changed. So g and tau can change even though you end up with the same superpotential using these linear combinations. And in particular, you can find that you can change tau to be these values, for example. So these transformations generate your duality transformations, and they form an S4 permutation group. This allows you to focus on a specific region in your tau space. So you don't need to take all values of tau. You can just focus on a fundamental domain, which is pictorially, which is pictured here. So at tau equals 0, we have this XYZ model down here, and the x cubed model now appears at tau equals 1, which is related by the duality to tau equals infinity. So we can study the entire conformal manifold by focusing only on this fundamental domain in the tau plane. What you'd like to do to large charge is to write down the effective action for this theory at large charge, assuming conformal invariance and all the symmetries and so on. So the problem is that unlike the x cubed model that we discussed before, the effective action is much more complicated here because we have 3 different chiral superfields. So in the effective action, there are many more possible terms that you can add. There's not just one term that you can add. So I've written down some examples of these allowed terms. So all of these are allowed by the continuous symmetries and by the scale invariance. You can also take into account some discrete symmetries that this theory has, but this is still not enough to make the number of terms finite. So you're always going to have an infinite number of allowed terms in the effective action. And so it is not enough in order to actually write down a useful effective action and try to solve the equations of motion and find the scaling laws and so on. So just using symmetries and scaling transformations and so on is not enough to make the problem tractable. So we're going to need to make some other assumption in order to be able to compute the dimension as a function of Q. The extra assumption we're going to make is we're going to use the Ethanol expansion. The conformal manifold that we discussed exists not only in 3 dimensions, but exists in any dimension between 3 and 4. So in 4 dimensions, the interaction is marginally irrelevant, and so we flow back to the 3 theory. So it's not really a conformal manifold, it's just a 3 point. In 3 dimensions, we have this full conformal manifold we discussed. And if you start in 4 dimensions and slowly raise epsilon, then a conformal manifold expands out of this free point and becomes bigger and bigger as you increase epsilon. So at leading order in epsilon, what you can actually show that this conformal manifold is a sphere. It is a sphere of radius epsilon, and it slowly gets bigger and bigger. And because it's a sphere of radius epsilon, a small epsilon, it is weakly coupled, because all of the different points are all a distance epsilon away from the free theory. So in the epsilon expansion, you can study this theory in perturbation theory in epsilon. So we're going to be thinking about this as fixing epsilon to be small and then varying tau across the conformal manifold in order to interpolate between this XYZ model and this X cubed model. To compute this minimal operator dimension for a fixed charge, and we're going to follow this paper cited here, where they explain how to do this computation at weak coupling or in the epsilon expansion. So they did this for the O2 model, and we're going to focus on this conformal manifold. The paper explains how to compute the scaling dimension in this double scaling limit. So we have terms in orders in epsilon, and each term is a function of these 2 double scaling parameters, lambda1 and lambda2. So in the original O2 model, there was only 1 double scaling parameter, this epsilon times q. But since we also have an exactly marginal operator taus, we also have another a double scaling parameter. We're going to focus on this double scaling parameter because this one tells us what happens as a function of tau as we cross the conformal manifold. So we're going to use this method to compute the dimension delta of q to subleading order in epsilon. It's a classical limit plus this one loop correction. The basic idea is to find a semi-classical saddle point once you include this background charge. The way this works is the following. To find this leading term, delta 0, what you do is you fix the charge, and then you solve the equations of motion in the presence of this charge. This corresponds just finding the different vevs for the fields. So each field is going to have some vev. Taking the solution, plugging it back into the energy density on the cylinder, you find the dimension, the corresponding operator in flat space, the state operator correspondence. Specifically, if you look for the ground state on the cylinder, you're going to get the smallest dimension at fixed charge. So we're going to be looking at the ground state energy as a function of these vevs. To get the subleading term in epsilon, the delta 1, we need to look at fluctuations around the saddle. Like Mark reviewed in the previous talk, what this means is just summing over Casimir energies of the different modes of the fields in your theory. So in the O2 model, there were only scalars, but in this example, we're also going to have fermions. So you sum over all of these modes, and this is going to give you this one loop correction to the classical result for the dimension. Let's start with finding the saddle, that's leading contribution delta naught. So solving the equations of motion at fixed charge, you find that there are 4 different solutions to the equations of motion written down here. This is already surprising. So in the O2 model or in the X cubed superpotential, there was always one solution because the theory is much simpler. But since we have 3 fields, we see that we allow for much more complicated solutions to the equations of motion. So clearly the question is, which one of these saddle points is the dominant one, is the global minimum? And this one will dominate and will tell us which saddle we have to expand around. So we plug this back into the energy and we find which saddle point is the global minimum. And it turns out that there's no one saddle point that is always a global minimum for any value of tau. So for different values of tau, we have a different saddle point that we have to expand around. In particular, around tau equals 0, where we had this fundamental domain, the saddle that is dominant is this one with only X getting a vev and the other 2 fields not getting a vev. But if we focus on tau equals infinity, some area up here, then we find that the symmetric vacuum with all 3 fields getting the same vev is the dominant one. So for different values of tau, we have a different saddle that is dominant. It turns out that this basically had to be the case because of the duality. So we said that you can reach any point on this conformal manifold by starting with the fundamental domain and acting with the duality. So the question is whether this solution, which is dominant in the fundamental domain, is invariant under the duality. So it's very easy to check that it is not invariant. And so if this is a solution in the fundamental domain, it cannot be the solution anywhere else. Its dual under this transformation will be the dominant solution. So in particular, you can show that all four saddles are dominant somewhere on the conformal manifold. So as a function of tau, they exchange dominance, and each one of them is the most dominant at some point. Like we said, we can just focus on the fundamental domain due to the duality. So we're going to focus on this saddle, and any other point can be reached by applying the duality, and the same result applies. So we're going to focus on just the saddle in the fundamental domain. Now we found the saddle to expand around. So we want to compute this expansion in epsilon. This is a long and boring computation, so I'm just going to summarize the main results and the interesting limits that we wanted to consider. There are three interesting limits. The first one is large epsilon tau, which is basically the x cubed model. So we expect to see the superfluid phase. The second one is small epsilon tau and also small epsilon q. Well, we expect to see this free scalar behavior because this is close to the XYZ model. And finally, there's an additional limit, which is also close to this XYZ model, where we take epsilon tau q to be small, but q epsilon to be large. So in this limit, we can go to the XYZ model, but we cannot go to 4 dimensions, which is a very nice limit. And we're going to look whether this also exhibits this free scalar phase behavior, whether delta goes like q. We're going to think of this as a consistency check for our results. Let's start with the superfluid phase limit. So in this limit, so close to the x cubed point, we do the computation and we find the dimension as a function of tau and epsilon. Let's compare this to what we expected to see in the superfluid phase. So we expected to see delta to go like q to the d over d minus 1. Plugging in d equals 4 minus epsilon and expanding in epsilon, we find this expansion. And comparing the two expansions, at least as a function of epsilon, we see that they match exactly. So we expect that if you compute the subleading terms in epsilon, you will eventually be able to resum these and get this full expression, just q to the d over d minus 1. And so the result we got is consistent with the behavior in the superfluid phase, at least to the order in epsilon that we computed it in. So close to the x cubed fixed point, we do see the superfluid phase. Now taking the opposite limit of going close to tau equals 0, close to the XYZ model, we do the computation and we find this thing. So let's go over whether this makes sense or not. So we expect that as we take tau to 0, we will be closer and closer to the XYZ point, and we expect the dimension just saturate the BPS bound. We expect delta to be linear in Q. And indeed, it's not immediate, but if you plug in tau equals 0 in this expression, you find that the second term vanishes and you're left just with this first term, which is just the BPS bound. So at tau equals 0 in the XYZ model, we reproduce the BPS bound and delta is linear in Q. In this limit, you can also take epsilon to 0. In this case, it's trivial that this term vanishes and you end up with the BPS bound, which again makes sense because as epsilon goes to 0, we're back at 4 dimensions, but the interaction is irrelevant and we flow back to the free theory. So again, we expect to be at the free scalar fixed point. And as a final check, the BPS bound is always a lower bound. And so you expect delta to always be larger than the BPS bound, even if it isn't saturated. And indeed, at least for Q larger than 3, the dimension we found is always larger than the BPS bound. But this is not always true for Q smaller than 3. So we're going to discuss this later on. Finally, we found one additional limit where you can still approach the XYZ model. Doing this computation, we find this result in this limit. And again, taking tau to 0, which means getting closer to the XYZ model, we find that delta saturates the BPS bound as expected. So this is a consistency check for this result. So I want to summarize just this calculation. What we found is that as a function of tau, we can interpolate between the BPS or the free scalar phase and the superfluid phase. So at small tau, what we find is that delta is linear in Q, so log delta over log Q is just 1. At large tau, we find the superfluid regime, so we find that log delta over log Q is 4 minus epsilon over 3 minus epsilon, which is just d over d minus 1. And as we look at this transition as a function of tau, we see that it's completely continuous. So there's no phase transition, there's no singularity happening as a function of tau. We just have a continuous transition between these two phases, between the free scalar phase and superfluid phase. So phase might be a misnomer because the transition is completely continuous. So now I'd like to discuss two interesting phenomena that we saw while analyzing this model, which we haven't seen in other places yet. So one neat thing is that the operator which has the lowest dimension changes as a function of tau. So in the O2 model or in the X-cube model, we always know what the operator is, or we expect that we know what the operator is with the smallest dimension. It's just 5 to the n, something very simple. But since we have 3 chiral superfields, there's now a lot of different operators that can have the lowest dimension. And the specific operator which is chosen is different for every point in the conformal manifold. This can be seen by just looking at the two limits. So if you focus on tau equals 0, which is the XYZ model, then we said that x to the q or y to the q or z to the q are BPS. And so they are the operator with the lowest dimension at fixed charge. While at tau equals infinity, the operator with lowest dimension is xyz to the power q. So since the operator is different in the two limits, we expect that the operator with the lowest dimension changes as we vary tau between this xyz model and this x cube model. In theory, you can do this computation in the epsilon expansion. It's not difficult. In order to actually find which operator is the one with the lowest dimension, we haven't done this computation, but this is already enough to see that it has to change with tau. It has to depend on where you are on this conformal manifold.
But this is a consequence of the duality, right?
Yes, you can also, that's right. This is also a consequence of the duality.
I mean, these are literally the webs that you had found before, right?
Right. Yes, I completely agree.
0 and then the other one, and then you said you dualized from one to the other, right?
Yes.
Okay.
Another interesting point is whether we can go all the way down to charges of order 1. So both in the O2 model and in the X-cube model, surprisingly, taking the results down to order 1, you found very good agreement with the numerics. So clearly we want to do the same thing and check whether this also occurs here. And in this model, it seems like things are more complicated. So we found two issues with taking Q to be very small. So we already discussed the first issue. So taking Q to be 2 or smaller, you find that the dimension is below the BPS bound, which does not make sense. Specifically, the dimension is an epsilon amount smaller than the BPS bound, which is very small. And so maybe you could still excuse this as just being a small correction to the epsilon expansion. And maybe this is corrected if you take higher orders and then take Q to be small. A bigger issue is by taking Q equals 3. So for any value of tau, it turns out that the specific value of Q equals 3, there is always a BPS operator. So for Q equals 3, you would have expected that the lowest dimension is always just the BPS dimension. This is the largest value of Q for which there is always a BPS operator. Plugging this into our results, we found that the dimension at Q equals 3 is larger than the BPS bound. It does not saturate the BPS bound. The reason why this is strange is that you can compare the results using the large charge expansion and the epsilon expansion to just Feynman diagrams, just the perturbative expansion Feynman diagrams. And in the previous examples this was done in, these matched term by term. However, in this result, in the Feynman diagram expansion, if you compute the dimension of the BPS operator, you should just find 0 corrections to every order. So it cannot be that it would match this result order by order in our parameters. There has to be some other type of correction here, which you would not see in this large charge expansion. So we have a guess as to where this comes from. Remember that we had 4 different saddles and they exchange dominance as you vary tau. And in particular, close to the edges of the fundamental domain, you would find 2 degenerate saddles. So it would not actually be 1 dominant saddle, but 2 saddles be very close together. In this case, the analysis might not be completely correct. So just taking a saddle point and expanding around it would not give you the correct result, because you would also have to take into account non-perturbative corrections coming from instanton corrections tunneling between the 2 saddles. So as long as you're in the fundamental domain and at large Q, you have 1 dominant saddle, which is enough, and you can just expand around it. But close to the edges, you would have to take into account these additional corrections. So of course, they're not important when Q is large, but if you want to take Q to order 1, you might also have to take into account these non-perturbative corrections, and hopefully they fix this issue at Q equals 3. And if you take them into account, you would see exactly the BPS bound being saturated. Okay, so let me summarize. So we just
But this is in principle doable, no? I mean, since you do
yes.
saddles, I mean, I'm not saying maybe it's not easy, but it's not. In principle, you have all the ingredients, or are you missing anything?
I have conceptual questions which I'm not completely.
Oh, sorry.
Sorry.
Am I back? Yeah. Am I back?
Sorry.
I'd love to discuss this. I'm very interested in this question. I'm not completely sure that this can be done straightforwardly. I'm still slightly confused about how to do this computation.
Okay.
Okay. We discussed this large charge expansion on a conformal manifold. We started as a function of the parameter or the exactly modular formation. We can interpolate between the free scalar phase and the superfluid phase in a continuous way. There was no phase transition function of tau. And we found these two neat phenomena at large charge. First, we found that the lowest dimension operator depends on tau, so it changes the different points on a conformal manifold. And we also found more than one saddle point, and that these saddle points exchange dominance as we move across this conformal manifold. So there are a few directions that we discussed that would probably be interesting. The first one would be to try to do this effective action formalism in the three-dimensional theory without having to use the epsilon expansion. Hopefully there's some other way to constrain the terms in effective action, and maybe if someone can make this tractable, and then you can really see the superfluid regime without doing the epsilon expansion. Another nice thing to do would be to see a transition between the free fermion phase and one of the other two phases. So we only found a transition between this free scalar phase and the superfluid phase, but it would be nice to see if this third phase is also continuously connected to the other two. I would also like to see more examples. We tried doing n equals 4 super Young Mills, which has a three-dimensional conformal manifold in n equals 1 terms, but this was a bit too complicated. It would also be nice to try to do the 3D Chern-Simons matter theories at large n. So these have a conformal manifold at large n, but I'm not sure one can do large charge in this case and still have a conformal manifold. The reason is that the conformal manifold exists only at large n, while for large charge you would do q larger than n, and it's not clear that these two limits exactly commute. So there's a bit of a question whether these theories are a good example of this. Finally, this instanton corrections, these non-perturbative corrections, are something that I would be very interested in discussing. So to see whether these corrections actually exist and whether they can fix the issue I discussed. Okay, thank you.
Thank you very much. Are there questions or comments?
I just had one small question to Adar. The free fermion phase exists in some patch, or it exists at a point?
I didn't have a free fermion phase. I had a free scalar phase.
Oh, sorry. Yes.
Yeah.
The free scalar phase.
It's not a function of. I mean, it depends on epsilon and q, right? So it really exists only at a point, but in some regime and parameter space, like the corrections are small enough so that you can still call this the free scalar phase. But I'm saying that if the corrections are small enough, if the leading term is still delta goes IQ, then you can still call it as a free scalar phase.
Well, how do you define a free scalar phase then? What is the definition?
I want delta goes like Q at leading order. So if epsilon here is small enough, then you can still call this leading term.
Okay, so you restrict to Q much smaller than epsilon, and then this definition might make sense. Okay.
1 over epsilon, yes.
1 over, I see. Thanks.
So I have a question about these transitions as a function of tau between the different saddle points. And so presumably because of these instanton effects, if you work at finite Q and do the transition, then it would be smooth as a function of tau. But if you work in the large Q expansion and you compute the coefficients, then are those smooth functions of tau or not?
Yeah, I'm not sure. I think a leading order in one of in Q.
Yeah, the leading coefficient is probably the same, but say the subleading coefficient is that a smooth function of tau or not?
Wouldn't it be?
I don't know the answer.
Wouldn't it be non-smooth when the saddles exchange dominance?
This is part of my issue, like about doing these computations.
Yes,
I
so
can
that
tell
was my
would be
question. Is it really
non-smooth.
not smooth, or do these instanton effects smooth it out, perhaps?
Okay, so maybe if you take Q to infinity, then it's non-smooth. But like you said, the finite Q, these have to be smooth. So this is part of my confusion about how to actually do these computations. Taking the Q towards infinity limit sounds like you're introducing some non-continuity, and then I don't know if the computation makes sense. I mean.